Hi guys, my name is Andrea Ferroni, and in this video I want to talk to you about DIDGMO. Since I seen posts somewhere on Facebook in the Didgeridoo community, I thought it was a good idea to give you some information about how to insert details and how to read the results. But first of all, the person who created this software left it freely on the net. There is a possibility to download it to use it standalone on your PC, but I never met someone who was able to run it in this way. So I suggest you to avoid to lose your time and simply use it on the net as it is. DIDGMO stands for Didgeridoo and Sound Modeling. So it's a software where you can describe the dimension of your didgeridoo simply editing the dimension of the length and the diameters. The first case I want to show you is not for to show in real what you can do with your didgeridoo, but to explain the graphics you find as a result. So in this case I designed a pipe that is 85 centimeters long with 40 millimeters diameter from the mouthpiece to the bell. I did it because it is useful to have the basic drone at 100 of hertz, like you see here. So in this first graphic, that is called the impedance spectrum, you find that, as in a previous video, you will find a link here to come back and to listen the explanation. With a cylindrical pipe, we have every odd multiple of the basic drone, we find a tooth. So if we have a basic drone at 100 hertz, we then find a tooth at 300 and then 500 and then 700 hertz. This is important to understand how they normally are in specific shapes. Then we also have to know that if we vibrate the lips in this position, so in the at the mouthpiece position, the lips are responsible to create a basic drone that is, or a first vibration that is tuned or have to be tuned at the same frequency of resonance of the pipe, so 100 of hertz. Doing so, the lips are even responsible to create overtones. They are all the multiples of the fundamental. So we find the first overtone or harmonic at 200 hertz, then 300, 400, 500, 600, and 700. In this case, you see that there is a slight difference between the numbers I'm telling you and the exact frequency of the ground spectrum peaks. This is because this software implements what it is called damping. I don't have so much time to explain deeply this point, but this is why there is this small, we could call it error. So very important is to understand that if we meet the harmonic of the lips with, we match the harmonic of the lips with the tooth, we have an amplification. If we match an harmonic of our lips with an anti-resonance, because between the two main resonances here, we have a range that is called anti-resonance. So everything that passes through it get out in a transparent way. So the same amount of pressure pass through the pipe without any modification. So it is not amplified at all. So this is why it is so small. So this blue area describes the color tone of your didgeridoo. So if you practice with this software for a while, you should be able to recognize the kind of color tone of your didgeridoo before to make it. In this other green graphic, you see the color tone of the tooth. This is important to know because a tooth is not a pure tone. Pretty anything in the nature is able to create a pure tone. So even if we play the tooth, that is considered sometimes an overtone, we also have his own overtones. In this area, we find the dimension of the pipe that I designed that is expressed in meters, when I usually prefer to talk in millimeters, but it's okay. We spend just 5 seconds more to write the numbers. The impedance peak area here describe in a better way this graphic, even because we have G, D, H, F. That they are the keynote of these frequencies. But we know that we can't be tuned exactly at the right frequency of the keynote. So in this case, we see that the frequency of 99 Hertz, I wanted to obtain 100, but this was the best I could make, is in G. And then we have a G in the 4th octave of the piano. The offset, so the error we have from the perfect tuning of a G is 17 cents of tone, and we have an impedance. I don't want to talk too much about this number because I consider that the higher peak means the highest admittance. Then we have the higher impedance between the peaks. Anyway, numbers are just to understand a little bit more the potential of every resonance. Then, as I told you before, even if the impedance peaks are a few, in this case till 800 Hertz we have only 4 peaks, when we look at the ground tone peaks we found more of them. This is because we have the resonances of the pipe plus that they can be well tuned, and so in a perfect ratio towards the basic drone, or maybe not. And we also have some other peaks. They are always in the perfect ratio between the basic drone, because this is typical for the sequence of the natural harmonics in nature, and they are made with the lips. So we have the resonances and the resonances of the pipe plus the harmonics of our lips. This is very, very important. Then we have the frequencies of the overblow. Okay, so then I try to make the same simulation with a didgeridoo shape that is not so far from a simple cylinder. And so I decide to take as example the didgeridoo. So the didgeridoo is made in yellow and black, And the yellow pipe has a little bit narrower dimension, and obviously the black one is a little bit larger, plus a short truncated cone at the end as a bell. And here it is. I tried to tune, I tuned the didgeridoo in E, and then I took the dimension. I measured the dimension of the didgeridoo 3 times using a caliber, and other measurements are made in a very good way. Anyway, these are the dimensions. We have to take, we have to consider the internal diameters of the instrument and even the internal length. Then, this is the internal dimension of the yellow pipe that goes inside the black pipe, and so this is why it looks longer and this looks shorter. And I was very surprised. This is why I measured this instrument 3 times. And given that the didgeridoo is pretty common instrument to have at home, maybe you can make a check. Maybe I made a mistake. Anyway, this was not the matter of this tutorial. Then I found as a dimension, as a first keynote, the D sharp. That is an alpha of tone lower than E. Anyway, given that it is pretty cylindrical, this instrument, we have the first tooth that is quite far, and so quite typical for cylindrical shapes. But then you can also see that the other tooths are not in the same ratio as from D sharp to A. Again, and this is why I gave you a first example before, we see that the first harmonic of our lips match with an anti-resonance, and this is why it is so small. Then the second resonance of the pipe meet the third frequency, the harmonic frequency of our lips, and this is why it is so amplified. The perfect resonance and the harmonic of the lips are described by this change of curve and this peak. In this case, even if we are very close to an anti-resonance, we are a little bit far from the exact frequency of the anti-resonance, and so this harmonic of our lips is amplified a little bit better than this other one. And so you can continue to analyze the ground spectrum. In this way, if you are trained to understand this stuff, you can understand better the kind of color tone of your didgeridoo. It is a quite long topic to be discussed, so I go on. Maybe you can write me privately if you need some more information, or maybe you can even decide to have a workshop maybe. In this green graphic, you find the overbow spectrum. And in this case, you find the frequency of the tooth and the related harmonic and inharmonic frequencies. Another information we find, it is the volume. The ground spectrum has frequencies in the horizontal line, and in the vertical line we have dB. That means it is a measure unit for the volume. But this can't be taken as a right information. It is just to understand maybe something, to have a comparison between the peaks. But it's not a useful information, because the volume is, for example, for this ground tone, the real volume can't be calculated with this kind of software, because here we have the resonances and we have the pressure of our lips. If they meet, if they match, they are amplified, and this is what we know. So they multiply each other, and we also need to know the exciting pressure inside of the pipe to be multiplied with the resonances. If we don't have the right pressure, we can't calculate the volume. Then again, we have the geometry dimension here, and the frequency expressed in hertz, the keynote, the octave, the offset, the impedance. It is very simple to recognize that this kind of shape, for example, has a D sharp basic drone in the 4th octave, that is a little bit lower than the right D sharp on the piano, for example, and the first tooth that is in the 6th octave. So it's a quite huge distance, is about 1 octave and a half. The 13th note distant from the basic drone. And then you can see other numbers. As I already explained before, I go faster on another example. Then the ground tone peaks, the first overblow peaks, and so on. You can also click here to download the paper to collect it in your PC. Okay, another shape I want to show you is the shape of my favorite E that I make from fiberglass. It's a didgeridoo shape that I started to create about 15 years ago. I made several small modifications, but it is still the same idea. And I tried to understand if we have the same error on this shape in terms of frequencies. And so this is the shape. It is 1 meter and 60 centimeter long, with 30 millimeters mouthpiece, and then it is made with truncated cones shapes. And in this case, I know the didgeridoo was tuned in E with a first tooth in E, and in this case it works perfectly. We will see the numbers later. Then we have the second tooth in C sharp, F sharp, A sharp, and so on. This means that given that the first two resonances of the pipe match perfectly the harmonics of our lips, we have two quite big peaks in the ground spectrum. Then we have another overtones, another harmonic of our lips that is close to 250 hertz, that doesn't match the perfect resonance. But given that it is even quite far from the anti-resonance, it is anyway a bit amplified. Then we find the resonance here, that it is, this is because the third and fourth harmonics are in the bell of the C sharp. This kind of curve that describe this peak with a round tip is able to amplify, maybe less if you are not well tuned, but it is still able to amplify. And so in this area we have a larger presence of harmonic components and inharmonic components, and then we continue ahead. We also have some peaks here around, and this is why I call this kind of shape a large spectrum. So the name of this shape is LSE shape, so large spectrum shape. We have again the green graphic where we see the color tone of the tooth, and then we can also see that it's richer than others because it has more components between 150 and 750 hertz. Then we can see how much is the error. It is only 9 cents far from the perfect E note. We have an E at the 4th octave for the basic drone and an E in the 5th octave for the tooth. And the error is even less. Anyway, this is the error on the software, and this is pretty the same error with simulation with other software I use at home and in my office. In this case, and so I made even other tries that I don't show you, I discovered that this kind of software works better if the shape of the didgeridoo come very closer to a standard shape of a didgeridoo. With shorter or with other kind of simulation like Helmholtz resonators that this software should be able to simulate, it doesn't work so well. I'm not able, and I don't want to waste my time trying to get into the code to understand what the creator did, and I suggest you to avoid it. If someone makes something online for free, it's important to just thank him. Here you see the ground tone peaks, and as before, please remind that the impedance peaks are related to the resonances of the pipe. Then the ground tone peaks contains the frequencies of the resonances of the pipe plus the harmonics made with our lips. And so this is why you see more frequencies than even you see here, because some of them looks pretty hidden, like this one, for example. And that's all. You also have the frequency of the overblow peaks, but this is it. So thank you very much for I've spent some time trying to understand my English that is not absolutely my first language, as you can imagine. I hope the information was enough clear for you. And if you have more questions, please write down, that is better, or if you want, you can even write me privately. Please think about to subscribe the channel, to thumbs up, and in this case that I don't ask so much, if you really think it's useful for your friends, please share this video on Facebook or whenever you prefer to publish it. Thank you very much. See you for the next video.